Okay, so meanwhile we can just reiterate. Uh, so last time we discussed time complexity of insertion sort and merge sort. And then we started some examples of DS. Yes, so in DS examples we did uh, basically binary search, both sequential and fast. And we introduced this problem of range minima, for which we haven't given a good solution, so we'll do this in the future. So let's now continue with a problem that we have seen before. And some of you asked how we will solve it, so now we'll give a fast algorithm. So we saw this iterative algorithm, iterative fib, which takes n steps and same space. Right, so using an array which will store the values of previous fi minus 1, you can calculate fi, and that you can do. So you can calculate the nth Fibonacci number in around n steps, which is much faster than, as we have seen, recursive algorithm. But I gave you this question of calculating in a super fast way for Fn mod 2024. Okay, and we can call this number m. I mean, this is the current year, but next year it will be something else. The point is that this, whatever is the year you want to calculate Fn mod m, so m will be very small, right? This is just a 4-digit integer. But f of n is extremely large. F of n has more than n. I mean, it is more than 1.5 to the n, so it has more than, it has around n digits. And assume n to be very large. As we said, n can be long int or long int, so it will be 64 bits itself. So this iterative fib will not work for this. The program will never stop. N steps will be too much. Right, so any ideas how you will calculate this? So matrix multiplication is what somebody says. It will be even better than that. We will actually convert this algorithm into a matrix powering problem. Okay, so you have to, ultimately I will design a matrix whose nth power mod m will give you the answer. And somehow that nth power of a number or a matrix, you can give a super fast algorithm. Okay, so super fast means log n. So it will work for n which is long n also. Yeah, so that's what we want to do in the end. But yeah, let's just for completeness or for revision, look at what the older algorithms will do. So this iterative fib, now it takes two arguments, right? N is the number which is extremely large, and m is for example 2024. It's very small. You just want to calculate the remainder. So how will you modify it fib n? So the addition will now be mod m. Right, we'll just store the remainder. So same pseudocode and same array. but now the arithmetic, the addition is mod m. Okay, which is an array which stores even smaller integers. Very small, it's only numbers from 0 to m minus 1 or 0 to 2023. So that's the array manipulation. In n steps, you will get the value of fn mod m. So let's record that. So this 8 fib n comma m requires greater than 3n instructions. I mean, the instruction is just addition, but then you also have to do division and compute the remainder. So it's a slightly more complicated instruction, but since m is small, this also will be fast. And only, so how much space is required for this? How much are you storing? So the array size is n, and each position in the array has to support this value up to m, right? So that is n plus log m. Not plus, actually, this will be product. Which is also fine because log m is very small. It's something like 11. So space is only 11 times n. Okay, so this space is also, I mean, space is not the problem here. The problem will only be instructions, because this when you convert this into seconds, it will be too big. So that is what is bad here. Yes. Yeah, this is just, we are just splitting hairs. We can skip log m, but if you want to see the dependence on 2024, you have to say log m. So when 2024 becomes, let's say, 2,24,000, then the amount of numbers that you can put in a position of the array will be bigger. So how much bigger? So that is basically binary representation of m. How many, what is the maximum power of 2 that divides m? That is log m. Because ultimately, everything in a computer is stored as 0, 1, right? I mean, if you are from electrical engineering, you know that the only thing a circuit can store is on or off state. So everything is ultimately reduced to 0, 1. So how many 0, 1s will 2024 require? So that in binary representation is optimal, that is log m. But that here is very small, so we can potentially skip it. So yeah, the time is linear, but it's still bad because our n is going to be very large. So it doesn't give a good time in seconds. And yeah, again, just for completeness, let's also check recursive fib, which is now n comma m. So this was if n is large, then you recurse. So which is n minus m and n minus 2. And with you have to do mod m arithmetic. Again, so here recursive fib n minus 1 comma m will give you a number between 0 to m minus 1. And recursive fib n minus 2 comma m will again give a number 0 to m minus 1. And when you add the two, this can be bigger than m. So you have to again take remainder. Okay, so this is again arithmetic being done. This is the instruction. So 2 calls of recursion and then 1 arithmetic instruction. So that will give you the answer. And the boundary condition you handle as base case, which is you just have to output n, 0 or 1, when n is 0 or 1 respectively. So this is much worse as expected. So this takes at least as many steps as is the value of f of n, the nth Fibonacci number. Right, because the recurrence that you get for time will be the same. Is the time for n minus 1 plus time for n minus 2 plus the additional arithmetic plus mod m. So, which is significantly bigger than 1.5 to the n. So this is really useless. Or somebody corrected it to n minus 1, I think. So it is growing exponentially. And n already was very large. So this is in the exponent n is setting. So this is even more infinite time. So yeah, now let us come back to the super fast algorithm that we want to do in this class. So that's the third idea. Right, so that's a clever insight which many of you have not seen probably. So the clever insight in many of the algorithms in this course will be do double instead of plus 1. Okay, so what does that mean? So instead of taking one step, you take double steps. So for example, in the recurrence, this fi equal to fi minus 1 plus fi minus 2, or even the recursion, you are reducing the problem of n to n minus 1, right? Or in other words, the opposite way, you are going from n minus 1, n minus 2 to n, so you are doing a plus 1. So instead of doing a plus 1, you should actually go from n to 2n. You should double, which in the opposite way means that if you want to calculate n, you should use n by 2. Okay, so instead of plus 1, you do double, or instead of minus 1, you halve. That will be the trick. And will of course, I mean, then what you have to do, what you have to see is you have to see the recursion in a completely new way, right? So Fibonacci sequence by definition is this. Is there a way to reinterpret this so that you can do the doubling thing or halving thing? You want to relate n to or I to I by 2. Yeah, so you have to really change the language in which you are doing this calculation. So let us change the language to a matrix. Yeah, and why do we do that, or how did we get this idea? This I don't know. This you have to ask the student. This is very mysterious, right? Why should you look at a matrix when you are only interested in numbers? Right, so that deep inside the student will tell you, but I can give you the solution. So the solution is that you write it like this. So you look at the evolution of I minus 1, I minus 2 locations in the sequence to the next locations, which is I and I minus 1. Right? So the evolution is given by a matrix. What is the matrix? So this is the 1, 1 row and this is the 1, 0 row. Okay, so this is the evolution of 2 entries in the sequence instead of 1 entry. So that's the matrix representation of the recurrence. It's completely equivalent. So evolution of F as a matrix. And in this case 2 by 2 matrix. So if you look at this evolution, then the advantage is the following. So we can call this matrix A and we can apply this again, right? So now from I minus 1, I minus 2, we can go to I minus 2, I minus 3. And what will happen? So what is the matrix here? Yeah, because the matrix, notice that the matrix here is an absolute constant. It doesn't depend on I or n or whatever. So this can be repeated. So you will get A square here. And now with the little imagination, you can see where we are headed. So you will get A to the n minus 1 times F1 and F0. This is in I notation. Is that correct? So this is then A to the I minus 1 times 1, 0. So what we have learned from here is that f of n is equal to the 1 comma 1 entry of A to the n minus 1. Okay, so the top left entry of this matrix, so this is a 2 by 2 matrix, you are powering it. So when you do this n minus 1 time, you still will have a 2 cross 2 matrix with very big numbers as the 4 entries. So the top left entry is the value of f of n, right? So same thing gives you the mod n value also. So this is our formula. We take this trivial matrix and we exponentiate it n minus 1 times. And each time we just store values, 4 numbers which are from 0 to m minus 1. Right? So every time the space is very small. And the formula is very explicit, so you can obviously do this in a for loop. It is just multiplying 2 matrices. But the number of steps here is still n, because the for loop has to compute each of these powers. Right? So where is the advantage? How do you make it super fast? By using repeated squaring. Yeah. So again, why do we do that? We don't know. You have to ask the students. So these are all deep insights. Right? It's hard to explain why we do this. But I have given you the main paradigm. It is you want to somehow double instead of just plus 1. So instead of just doing a for loop with increment of plus 1, you want to take a larger leap. So what you see here is that instead of computing a square a cube, from a square you can directly go to a to the 4. Why is that? Well, if you have a square matrix, you can just square it again, so you will get a to the 4. Right? So you can skip a cube. And when you are at a to the 4, you can skip what? You can skip 5, 6, 7 and go to 8, because a4 you can just square. So only by doing squaring you can calculate this. I mean, of course, the smart ones amongst you will ask that what if n minus 1 is not a power of 2? What will happen then? right? So what will happen if n minus 1 is 7? Then you cannot skip 7. If you skip 5, 6, 7, then you go to 8 and you only have 4 and 8. How do you calculate 7? Yeah, so the even more smarter ones amongst you will see that what you have to do is n minus 1 you have to write in binary. So it's a sum of 2 powers. And then only those 2 powers you have to calculate. Right? So 7 you have to write as 1 plus 2 plus 4. And so you get a, then you square it, and then you multiply those. So 1 plus 2 plus 4 will give you 7. So that's how it is done. So let us note that. So the insight of squaring don't multiply when you can square. Right, so what you do is you calculate these powers. So a square, a to the 4, a to the 8, a to the 16, and a to the 2 to the k, everything mod m. Right, so the arithmetic always is mod m so that the numbers do not blow up. So all the entries of these 2 by 2 matrices will be very small. They are only between 0 to 2023. And there are only k steps here. Right? So for the price of k steps, you are getting a power of 2 raised to k. Right? This is the power of doubling instead of plus 1. And which shows in the exponent as squaring. Right? So it's happening in the exponent, so this is actually the power of squaring. This is called repeated squaring. So yeah, let us just, if you have not understood the details, you can work out the pseudocode. So let's just make some observations first. So first observation is that we are getting to 2 raised to k power in k steps. Right? So this is why it is a super fast algorithm. For you are reaching nth power in log n. So it's something like binary search, but far more complicated. It's not just a matter of sorting and looking at the midpoint, right? This is much more complicated arithmetic. So which means in our case that we get to n minus 1th power of the matrix. Equivalently, we get to f of n mod m in log n steps. Log n, or maybe just the ceiling of that, the integer after log n. So this is what you have to remember. Okay, some more small observations we'll need. So how do you multiply matrices? So recall, if this if B and C are two 2 cross 2 matrices, how many steps are required? No, 3 is being too stingy. I mean, the matrix itself has 4 entries. You have to see all entries. It's slightly more. It's 4 square plus 4. 4 square plus 4, let me say instructions. So assuming that this addition multiplication is for free of numbers, when you have two cross two matrices, you see that there are 4 entries each. So every entry you have to multiply with every entry, right? So that's 4 square, and then you have to do some additions also. After you have multiplied, you add. So it's around 4 square plus 4 instructions, but then each instruction itself is adding numbers modulo and then dividing and finding the remainder modulo m, right? So if m is growing, then that is again log m, another cost of log m. So it's around 20 log m time, let me say. So in terms of simple steps, it is you can multiply 2 matrices and also calculate the answer modulo m. So the output will just be 4 integers between 0 to m minus 1. All that you can do in around 20 log m steps. Okay, so this is considered very cheap. This is not our bottleneck, but still you have to be careful about this. So how much will this cost? A raised to 2 raised to k mod m. So this 2 raised to kth power we have written above, right? It's k steps. It's basically k squarings. Each squaring you will do like b cross c subroutine. You will call that subroutine k times. Correct? So it's that answer times k. So let me put it like that, 20k log m. Okay, this is the complexity of calculating a raised to 2 raised to k mod m. So these are the basics of our pseudocode, right? Do repeated squaring. Each squaring costs around log m, and then you repeat this k times. So you will get to a raised to 2 raised to k mod m. Okay, so any questions at this point? So whatever you did not understand here, you check as an exercise. Because these are the things which will be, which I will just assume, and you will be asked questions in the assessments about this. Okay, these are the very basics of pseudocode analysis. So now let us write down this clever fib n comma m. Maybe one more remark can be made here. What is the space which is required for this calculation? A raised to 2 raised to k mod m. How much space is needed? So each time you only have to store 4 numbers, and that too modulo m, right? So the space is just 4 times log m. So the space here is trivial. This is just m is 2024, so it's around log m is around 11. So 44 bits are all you need to store. Plus there will be some overhead of your device, but removing that overhead, your requirement is only 44 or 50 bits, right? Yeah, every space can be reused. And first of all, I mean, there is no recursion here. It's a for loop which is just going from E4, 8, 16 to 2 raised to 2. Every time the same space you can reuse. The previous space you are just, whatever is written you are squaring. Right? So the space here is almost 0. There is no space requirement in this algorithm. So it's a super fast algorithm with almost 0 space. Right? So these are dream algorithms. Okay, so yeah, let us get into more details of the pseudocode. So we'll keep the we'll maintain an array S which will store your matrices. Yeah, actually this algorithm will have more space requirement, but we'll see that later. The previous statement was still right. So let's initialize the array with the matrix A, which is defined, if you remember, 1, 1, 1, 0. And let us take k here to be, k we will take log of n minus 1 ceiling. So this is the maximum power of 2 that we want to reach, right? We want to calculate a raised to n minus 1. So S0 I have substituted to be a, and so as I have said before, n minus 1 you have to first write in binary so that you know which two powers are important. So n minus 1 will define this binary representation. Or won't even go to k, it's k minus 1. So this n minus 1 has maximum k bits when you do base 2 representation. So you calculate the binary representation, this B0, B1, B2, Bk minus 1 are 0, 1. So write this in binary. And so now so some of these B's are 0 and the others are 1. So the zeros we don't care, the ones, for example, if B2 is 1, then it means that a to the 2 square has to be calculated. And if Bk minus 1 is 1, then it means that a raised to 2 raised to k minus 1 has to be calculated because it contributes to a to the n minus 1. Right? So the bits here that are on, you have to calculate those powers and multiply them. This will be the value of a to the n minus 1. So the powering we will do as promised before by this for loop, repeated squaring k times. So we can do that in using the array. So Si will just be Si minus 1 square mod m. Okay, so that is repeated squaring. So whatever was calculated before, that matrix you square mod m. And so this will create your array S0, S1, and so on. By the way, the array is correctly ordered. So this basically is a to the 2 to the 0. Right? So a to the 2 to the 0 is stored in S0, and then in S1 we will be storing a square, a to the 2 to the 1, and so on. Okay, so Sk minus 1, I think I don't need K minus 1 is fine. That would give you a to the 2 to the k minus 1 in the end. So the array will be full, the S array, and which will give you the things that you need. So you need S0 to the B0 multiplied by S1 to the B1, Sk k minus 1 to the b k minus 1, everything mod m. What is this? So what is b now? So by the for loop, correctness of the for loop, you get that S0 is e to the b0 and S1 is S1 to the b1 is e to the 2b1 dot dot 2 to the k minus 1 b k minus 1. So this is nothing but a to the n minus 1 mod m. Okay, so this b that we have calculated by taking a product of essentially array elements, which are matrices, is the answer that you want. Right, so this answer you output. So you just return b, that's the end. That's the matrix mod m, matrix power mod m, but 1 comma 1th entry, that is Fn mod m. Okay, so this matrix's top left corner is the nth number reduced modulo 2024. That is the answer. So this is the full pseudocode. Obviously, if you convert this into a C program, it will be much longer, but I don't have the energy to give you the C program here. So that you have to do. So as I said, I'll make my things simple and your part hard. Right? So I'll give you the simple pseudocode, then you implement it in C and see whether everything actually works. But the nice thing about writing it first like this is that you can very quickly do a back of the envelope calculation for time complexity. Right? You can see that broadly the C program will be doing this, and so you can give a good estimation of the time complexity, how fast or slow your algorithm is, how good or bad. So let us do that. Any questions about this pseudocode? This generally will be the modus operandi. I will give you pseudocodes only at this level, not in further detail. Okay, so you have to understand this when you go home. But if you have quick questions, you can ask. Any step that you don't understand, what is the meaning of these arrows and the backslashes in orange and all that? Do you understand everything? Okay, so after this it will only get harder. So let's first make the time complexity statement. So clever fib takes only so let's put a guess here. So 20k log m was the number of steps or time for calculating this last power, right? So let's write that down. So 20 log m times k. So k means k is log n. Right? So this is the time complexity. 20 log m times log n is the time complexity to compute the last thing in the for loop. To basically cover the for loop, it takes you that much time. But the pseudocode has more, right? The pseudocode also multiplies to calculate b. It multiplies those things in the array, and so that is kind of another for loop. There are two for loops here. So this is a for loop, but this is also a hidden for loop. Because what I have written in the second line after the for loop, that you really cannot, I mean, if you do it in a C program, you cannot compute it immediately, because you don't know what k is. K is some growing, something which depends on the input. So the only way you know is you have to do another for or while or some loop, right? So that loop will have k steps. So it's basically 2 for loops, each has k iterations. So you get double of that. So it's double of that. So this is the amount of time. So it's around 40 log n time or steps. And what is the space? What is the space requirement here? So array is the biggest space consumer here. Array has k log m data. K is around log n. So this is around the same space. Okay, but both these values are extremely small. This is a super fast and very small space requirement. Right, log m you can ignore because it's just 11. So both of them are just log n time and log n space. Yeah, so even when n is 2 raised to 64, it will be very fast. It's a fast algorithm. You can implement it on your smartphone. So this is happening because this is a logarithmic scale algorithm. And so we have achieved something in logarithmic scale which is much smaller than the linear scale, which was around n, which is much smaller than the exponential scale, that's 2 raised to n. Okay. So super fast will be logarithmic, that we have achieved. Linear was iterative fib and exponential was recursive fib. So you have seen the whole spectrum. This is the spectrum of almost all the problems which you will face in your future. In practice, in engineering, or in this class, all the problems will be in this scale. You will almost never face a, I don't think you will ever see a problem which will require more than exponential time. And again, it will be rare to find a problem where you will have a faster than logarithmic time. Okay, this will be the scale of your efficiency and inefficiency. So this is usually written log n, this is n, and this is 2 raised to n. N is the input size. Any questions? Okay. Yes, so this discussion till now necessitates formalizing time complexity, where we don't have to worry about this factors of 20 and 2 and so on. So for that we'll need a proper notation. So let us try to formalize it a bit. So time complexity of a pseudocode or an algorithm. So it is defined as it's the number of instructions required in the worst case. As a function of the input size. And usually input size we'll use the variable n. Okay, n will be our favorite variable to mean input size. Input size is just when you write a C program and it takes an input from a file, what is the size of the file? Okay, that is all which n denotes, or what we mean by input size. So file is measured in bits or bytes, and that is basically what your input size is. And output size will be similar. If your C program takes input from a file and puts input in another file, what is the size of the output file? Right? So these are the input-output sizes. Everything that we discuss, complexity or functions or whatever, are functions of this n. Now the one important thing here is worst case. If you are not experienced, so generally this is a tendency of students that they write a program only to pass the test cases, right? So they say that for this case my algorithm is very nice and beautiful and fast, so I should get full marks, right? This is the logic. So for that I have underlined worst case analysis. So worst case is against your feelings. So you have to give an algorithm which works for all inputs, okay, whether it is given to you in a test case or not. So the algorithm that you give, when you say that it's a fast algorithm, it should be fast for all cases, which means in the worst case, so you should always think adversarially. An adversary is giving you an input, and your algorithm has to behave as you are saying it is expected to behave. Okay, so that is the analysis which we do in this course.